Hello everyone, welcome to the video. Today we are going to solve the problem longest common substring. In this problem, we are given two strings and we have to return the substring which is common to both the strings and whose length is longest. We have to return the length of such substring. In the previous video, we solved this problem using top-down dynamic programming approach. In this video, we will solve this problem using the bottom-up dynamic programming approach. We will also see a space optimization of the bottom-up approach. We are going to solve this problem today. We will go through the thinking process, write the algorithm, and then also see a working code for the same algorithm. Later, we will also see how to return the actual longest common substring and not just its length. So before we start, if you are new to this channel, please don't forget to subscribe and press the bell icon. Let's start. To begin with, let us first note the key things given in the question. We are given that there are two strings and we have to return the length of the longest common substring. What does that mean? Now we know what is a substring. Substring means a contiguous part of a string. So it has to be a substring. Then it has to be a common substring. That means this substring should be present in both the strings given. And then it has to be the longest as well. That means out of all the common substrings that are present in both the string, we have to return the longest one. And we have to return the length for it. So let us consider this example. We are given two strings A, B, C, D, G, H and A, C, D, G, H, R. In this string, the C, D, G, H, this substring is common to both the strings and this is the longest common substring here. So our answer that we will return is 4. So if we consider our solution as a black box, we are getting two strings as input and we are returning a length as output. One thing that we may have to note here is that it is possible that in the two strings given, there is not even a single character common. In that case, we should clarify with the interviewer that what should we return in such a case. The interviewer may say that in such a case you can return -1 or something like this. So based on this now black box representation of our problem, what will our function signature look like? Our function signature will look something like this. Before moving to the bottom-up approach, let us first briefly recap how did we solve this problem using top-down approach. So first of all, we made an observation. What observation? We thought that whatever is the substring that we are looking for, example CDGH here, this substring will end at some or the other index. So we knew that if it ended at index I in first string and it ended at index j in the second string, then we could also consider that this substring is the longest common suffix for the strings ending at I and j. Basically for strings ABCDGH and ACDGH, the longest common suffix for these two strings is CDGH. This gave us the idea of calculating the length of the longest common substring. We thought that we can iterate for every I and every j. Then for every such pair of I and j, we could calculate the length of the longest common suffix. Now, whatever is our longest common substring, it will be maximum of all such longest common suffix that we get. So this way we could calculate the longest common substring. Now our problem became, how do we calculate the longest common suffix for a pair of I and j? Now what did that mean? This meant that we are considering the first I characters of string S1 and first j characters of string S2. Then in such a case, what will be the length of the longest common suffix? Now we thought we can solve this using recursion. We will first check the last characters. Now if we are considering first I characters of S1, where will the last character lie? It will lie at I minus 1. And similarly, if we are considering the first j characters of S2, where will the last character lie? It will lie at j minus 1. So we first compare the last characters. If the last characters are equal, then our answer is simply the length of longest common suffix for I-1, j-1 plus 1. Because the last character is already equal, so we calculate the same thing for the remaining strings. Basically, for first I-1 characters of S1 and first j-1 characters of S2. We calculate the length of the longest common suffix, and plus 1 is there because the last character is equal. And if the last character was not equal, then obviously there is no suffix which is common to both the strings, so the length of the longest common suffix will be 0. So this was the recursive relation that we have derived for calculating the length of the longest common suffix. Now, as per the algorithm, for every pair of I and j, we called this method, this recursive method, that calculated the length of the longest common suffix. Now the maximum among these will be our final answer. Now in the recursive method, we had the inputs S1, S2, I and j. I and j represented the first I characters of S1 and first j characters of S2. Therefore, we had already done the two steps, identifying recursive relation and identifying the inputs to the recursive method call. Next, we tried to convert this recursive relation into the algorithm here. It was as already discussed. We first checked the last characters. If they were equal, we got the answer for our subproblem. Our answer for I and j will be subproblem answer plus 1. And if the two characters were not equal, our answer would be 0. We would return that answer. But this itself was not complete because this method would go on infinite recursion as it keeps calling itself. So we needed something called as base or terminating condition for this recursion. The base or terminating condition usually happens when our input is smallest. Now our input smallest meant I is equal to 0 or j is equal to 0. I is equal to 0 means that we are considering the first 0 characters of S1, which means that the first string is empty, and j is equal to 0 means we are considering first 0 characters of S2, which means second string is empty. Now if any of these strings, any of the two strings is empty, then we know that the length of the longest common suffix will be 0. So we added this base condition. Now our algorithm was complete, but it had high time complexity because there were overlapping problems. We solved this problem using map. We stored the answers for every pair of I and j in this map, and before actually returning the answer, we put that in the map. Now next time, whenever there was an input, before calculating, we first checked in the map if we have already seen this input. If we have already seen this input, we did not calculate again, but returned the answer directly from the map. So this completed our top-down dynamic programming approach to this problem. Now next step is thinking about the bottom-up approach. But why do we even need to think about bottom-up approach? What is the problem in top-down approach? The problem is recursion. In recursion, as the recursion tree grows larger, the number of method calls also grow larger, and every method call occupies some space in the memory. So since with recursion, the number of method calls are large, a large space in memory is occupied, which is not good. We don't want that. So ideally, we would like a solution that could solve the same problem in a similar time and space complexity, but does not involve so many method calls or does not involve recursion. That is why we need to think of bottom-up approach. What do we mean by bottom-up approach? In the top-down approach, as the recursion progresses, we move from solving for larger inputs to solving for smaller inputs or our base conditions. In bottom-up approach, the order is reversed. We first solve for the smallest of our inputs for our base conditions, and then gradually we move upwards till we reach and the solution for the problem that is given to us in the question, the largest input. We still use the insight of the recursive relation, we still use the answers of smaller problems to get the answer for larger problem. It is just that the order is reversed. This means we still have to store this information that for a pair of I and j, this is our answer. Now we need to store this information and we need to be able to iterate from smaller input to larger input. We need to be able to iterate from smaller values of I and j to larger values of I and j. So what data structure can we use here? We can use a two-dimensional array. One dimension can represent the string s1 and another dimension can represent the string s2. So we have noted down here that we are using a 2D array. Now, as per this recursive relation, we will iterate from I is equal to 0 till I is equal to n, because we will consider from first 0 characters till first n characters for string s1. Similarly, we will consider first 0 characters till first m characters for string s2, where n and m are lengths of both the strings. So what does this suggest? What does this suggest? That our dimensions of the matrix should be n plus 1 cross m plus 1. Now, what does any position in the matrix I comma j represent? Any position in the matrix I comma j represents that we are considering first I characters of s1 and considering first j characters of s2. And what will the value at any such position represent? The value at any such position will represent the length of the longest common suffix for such I and such j. So if we have this matrix filled, what is the relation of this filled values to our final answer? How can we get our final answer from this matrix? We know that the longest common substring is basically the length of the longest common suffix that we find for I comma j. So if this matrix is filled, the maximum value in this matrix is our answer. So while filling this matrix, if we can keep track of the maximum value that we see, our job will be done. So now we have noted that our final answer will be the maximum of all the matrix values. So now how do we fill this matrix? How do we fill the value at any position I comma j? We know that to fill the value at any position I comma j, we need to first check if the last characters in the two strings are equal. Since we have I and j, it is very easy for us to check that. Now let's say they are equal. Then what should we do? Then we should look for answer for I minus 1 and j minus 1. Now if I comma j is this, then where will I minus 1 and j minus 1 lie? This will be I minus 1, j minus 1. So what will we fill at I comma j? We will fill this value plus 1. And if the two characters were not equal, we will simply fill 0. This also means that we can fill this matrix row wise. That way, when we reach at I comma j, we will have all the values that we need. So we have noted here that we have to fill this matrix row wise. Okay, so now we know how do we fill the value at any position in the matrix. So now we know how to fill this matrix out, and we know what will be our final answer. But how do we even begin? From where do we start filling this matrix? To start filling this matrix, we need to think about our base conditions. What are our base conditions? Our base conditions are when our inputs are smallest. So it corresponds to I is equal to 0 and j is equal to 0. Now what do I is equal to 0 and j is equal to 0 correspond to in this matrix? They correspond to first row and first column in this matrix. Now let us try to understand what does I is equal to 0 mean. I is equal to 0 means that we are considering first 0 characters for S1. Basically, we are not considering any character. Now if S1 or if the first string for us is empty while calculating the length of the longest common suffix, then we know that the answer for the length of the longest common suffix will always be 0. Therefore, we fill our first row with 0. Similarly, j is equal to 0, that corresponds to our first column, means that we are considering first 0 characters of S2. That means the answers here will also be always 0. Okay, so now we know how to begin filling the matrix, we know how to fill the value at any position in this matrix, and we know that our final answer will be the maximum of such values. So we have everything that we need to convert our thoughts into algorithm. So let's try doing that. Clearly, we need a two-dimensional array of size n plus 1 and m plus 1. We will fill its first row with zeros and its first column with zeros as well. Now our aim is to keep on filling this matrix. So we will iterate. We will iterate for I is equal to 1 till n, and we will iterate for j is equal to 1 till m. Now our aim is to fill the value at any position I, j. We will first check, as per this recursive relation, if the last characters are equal. If they are, then we know that the value at I and j will be equal to the value at I minus 1, j minus 1 plus 1. And in the else case, if these two are not equal, the value will be 0. But we need to do one more thing. We need to keep track of the maximum value that we see here at any I, j, because that maximum value will be our final answer for length of longest common substring. So we have another variable max so far. Its purpose is to keep track of the maximum value that we see at any I, j. So we initialize its value with 0, and anytime we see something which is greater than max so far, we update our max so far. And finally, we will return our max so far. This completes our bottom-up dynamic programming algorithm for this problem. Now, what will be the time complexity and space complexity for this approach? Time complexity will be big O of m into n, because for every pair of I and j, we are calculating the answer just once. And the space complexity will also be big O of m into n, because of this matrix where we are storing the answer for all of these combinations. Let us now go through the code for the same algorithm that we just discussed. You can also find the link to this code in the description. So this is our main function, which is supposed to return the length of the longest common substring. It takes as input the two strings s1 and s2 as well as the lengths of the two strings. So first of all, we declare this two-dimensional array of size n plus 1 cross m plus 1. Then we fill its first row with zeros, and then we fill the first column with zeros. Next, we have to iterate for every I and j, and we have to fill the value at every I and j. So we iterate for I is equal to 1 till n and for j is equal to 1 till m. To fill the value at any I, j, we first check the last characters. Now, for the last character at I will correspond to character at I minus 1 position in the string, because here I represents the first I characters considered. So if we are considering first 3 characters, then the third character lies at index 2. Therefore, we compare the two last characters at I minus 1 and j minus 1. If they are equal, then we know that the value at I, j will be equal to the value at I minus 1, j minus 1 plus 1. And also, to return the length of the longest common substring, we need to keep track of the maximum values that we see in this I, j. So there is a variable for this purpose, max so far. We initialize it with 0, and then whenever we see that this value is greater than the max so far, we update our max so far. And if the two characters were not equal at all, then there is no longest common suffix between two strings. So the value at dpi, j is 0. And finally, we will return the max so far, which will hold the length of the longest common substring. So this completes our code of the bottom-up approach for the problem longest common substring. There could be an extension to the problem as well. We could be asked to solve this problem in lesser space complexity. The previous solution had the space complexity of big O of m into n. Why? Because we were using this two-dimensional matrix. Let us see if we can do anything better. To see if we can do anything better, let's see if we really need the whole matrix at any point in time during the solution. Let us say we are filling the value at this point I comma j. Now to fill the value at I comma j, what do we need? We need this value. This value is the value at I minus 1 comma j minus 1. Now even if there were 1,000 rows above this row, we wouldn't care about those values while we are filling this I comma j. So we can say that while filling this current row, at max we need the answers for this previous row and nothing above it. So maybe we can try solving this problem using two one-dimensional arrays or two rows. Let's say these are the two rows, previous and current. Current is the current row that we are filling and previous corresponds to the row prior to it. Now if we can solve this problem using only these two rows instead of using the whole matrix, we would have optimized the space complexity. Now let us see how can we solve that. First of all, let's just understand what do current and previous denote. The current row, let's say, corresponds to the first I characters of string S1. Now if current row corresponds to the using first I characters of S1, what will previous row correspond to? The previous row will correspond to using first I minus 1 characters of string S1. And what will be the dimensions of this current and previous row? The dimensions will clearly be m plus 1, just like this. So we have noted that dimension of the two rows is m plus 1. Now let us understand what does any position j correspond to in this row. This position will correspond to using first j characters of string S2. And what will the value at any such position will correspond to? The value would denote the length of the longest common suffix if we are considering first I characters of S1 and first j characters of S2. So if we can fill these up, the previous and the current row, from row 0 and 1 to 1 and 2 to 2 and 3 to 3 and 4 to 4 and 5 and to 5 and 6, then whatever is the maximum value that we encounter, that will be our answer. So we have noted that our final answer will be maximum of all as we go on filling the previous and the current rows. Now let us try to understand how will we fill the value at any position current j. Now to fill the value for position j, that means to find the answer for the two strings where we are considering the first I characters of S1 and first j characters of S2. To find the length of the longest common suffix for such I comma j, we need the length of the longest common suffix for first I minus 1 characters of S1 and first j minus 1 characters of S2. Now I minus 1 characters of S1, that means the answer will lie in the previous row, and j minus 1 characters of S2, that means the answer will lie exactly here. So to fill the value at j, if the last characters are equal in the string, we will simply add 1 to this answer and we will fill it here. And if the last characters were not equal, then we can simply fill 0 here. That means we now know how to fill the value at any I comma j. Now let's see what happens when we move from one iteration to next. When we move from one iteration to next, our previous will be of no use and our current will act as previous in the next iteration, and we will be filling out a new current. So we have here noted down that previous will point to current at the end of every iteration, and in every iteration we will be filling out a new current. Okay, so now we know how to fill the rows current, and we also know how to update the rows in every iteration. But how do we even begin? We will begin from here, rows 0 and 1. We know from the base conditions that the first row and the first column will be filled with zeros. So initial values for previous row will be 0, and for every current row the first element will be 0, as can be seen from here. Okay, so now we know how to start filling the two rows previous and current. We know how to fill the two rows at any position at any iteration. We know how do we update them at any iteration, and we know how do we derive our final answer while filling these rows. So we have everything that we need to convert these thoughts into algorithm. So let's try doing that. So we clearly need a new previous array of size m+1. So we first declare that. Then we initialize it with zeros, as this corresponds to the first row here. Now we have to iterate and fill the current row in every iteration. So we iterate from I is equal to 1 till n. And here in every iteration we will fill up a new current array. So we declare a new current array of the same size. And we know that the first element of every current array will be 0, as it corresponds to the first column. Now we have to fill up this current array. So we will again have to iterate from 1 till m. In every iteration here, our aim is to fill the value at current j. So as per the previous algorithm, we first check if the last characters in the two strings are equal. If they are, then we derive our answer for current j from the previous array, as we have discussed. Rest of the steps are quite similar. We need a variable max so far to keep track of the maximum value that we have seen. If the value at current j is greater than this, then we update the max so far. And if the two characters were not equal at all, then the value at current j will be equal to 0. Thus, when we are done filling the whole current row, we will move to the next iteration for this loop. Before moving to next iteration for this loop, we will point our previous to current, because now our current will act as previous in the next iteration. And finally, we will return the max so far. This completes our bottom-up approach of solving this problem, which is also space optimized. Now what will be the time and space complexity for this approach? The time complexity will still be big O of m into n, because we are still finding the answer for every combination of I and j. But the space complexity is just order of m, because we are only using two arrays, previous and current, whose sizes are of order of m. So this way we have bettered in our space complexity from previous solution. One may think that since here in every iteration we are initializing a new current array, that means our space complexity should be order of m into n. But that's not the case. Let's see how. Here we first declare the previous array. That means a new memory block is allocated and a pointer previous is pointing to that block. Next, we declare a current array as well. Another memory block is allocated and a pointer current points to it here. Then we go on filling the values in current array. And here, when we are done filling the current array, we point our previous to current. Let's see what happens here. Here, the previous connection of this previous pointer to this memory block is broken, and now this pointer points to this memory block. Now there is no way that our program can reach this memory block. So whatever is the garbage collection mechanism of the language that we are using, that mechanism will free up this space. Now this is the case that current and previous both are pointing to the same memory block. Now let's see what happens in the next iteration. In the next iteration, we again declare a new current array. Then Another memory block is allocated and now this current pointer points here. That means this connection is broken, but previous now points to this memory block. And this goes on in every iteration. So therefore, at max, we only have two arrays of size m plus 1. And that is why our space complexity is just order of n. Let us now go through the code for the same algorithm that we just discussed. You can also find the link to this code in the description. So this is our main method that is supposed to return the length of the longest common substring between the two strings. It takes as input the two strings s1 and s2 and their lengths n and m. So first of all, we declare a new array previous of size m plus 1. We initially fill it with the values 0 because these correspond to first row of the matrix that we had done in previous solution. Then we have to iterate. In every iteration, we have to fill the current row. So we iterate from I is equal to 1 till I is equal to n. And since there is a new current row in every iteration, we declare a new current row of size m plus 1. Now, the first element of this current row is 0 because this corresponds to first column of the matrix that we filled in the previous solution. So we fill the current row value current 0 equal to 0. Then we have to fill all the values in current row. So we iterate from j is equal to 1 till j is equal to m. We first check if the last characters at the two strings are equal. If they are, then our answer will be equal to previous of j minus 1 plus 1. Previous of j minus 1 corresponds to the case when we are considering j minus 1 characters of s2 and I minus 1 characters of s1. Therefore, we will get the value at current j. Then we need to also keep track of the maximum value that we see because the maximum value is our answer. So we have a variable for that. So at any point in time, if this value becomes greater than max so far, we update this variable. And it was initialized with the value 0 earlier. Also, if the two characters were not equal, then we know that there is no longest common suffix. So we fill the value current j equal to 0. Once we are done filling the current row, we have to move to the next iteration. But before we move to the next iteration, we have to update our pointers. Now this current row will act as previous for the next iteration. So we point our previous to current. And the memory block that this previous was earlier pointing to, that is of no use to us. So that will be cleaned up. And similarly, we will iterate and we will keep on filling and we will keep noting and updating the max so far. Finally, we will return the max so far. So this completes the code for the space optimized version of the bottom-up dynamic programming for longest common substring. Let us now see our code in action. We are giving it one test case as input. The lengths of the two strings that we are giving are 6 and 6. The first string is ABCDGH. The second string is ACDGHR. Let's see what is the length of the longest common substring that our program returns. It returns 4. So far, we have been focused on returning the length of the longest common substring. But there could be an extension to the problem as well. We could be asked to return the actual longest common substring and not just its length. How will we do that? So we already know the length of the longest common substring. That length will be the maximum value that this variable max so far takes. So if we somehow know the starting position or the end position in either of the strings, then we will be able to point out what is the substring. So how can we do that? Now here we know whenever we are updating this max so far, we are now pointing to the longest common substring. So at this point, if we also note down the j, then this j will correspond to the end position in the second substring. So now we have the length, we know the end position, so we can always return the actual longest common substring. This is it for this video. If this video was useful to you in any manner, please let us know by commenting below. Also, let us know in the comments what will be the next problems that you would want to see on this channel. Please don't forget to like and share the video and subscribe the channel. We will meet again in the next video with some other problem. Thanks for watching.